How's it going, everyone? I'm Jason Lopatecki from Arize AI, observability evaluation, one of the leaders in this space. Excited to talk to you today about prompt learning, which is something we put out research on, probably started about 6 months ago. We've been putting out continuous research since, and happy to make this interactive, talk about our view of this. But the vision for this isn't just us. I hear it out in the ecosystem a lot, so we'll try to introduce you to the subject. I think the first thing a lot of us feel out there who are building agents and assistants is a lot of them aren't working. So if you're at the application layer, which is a little higher than a lot of the stuff you see here, making this stuff work, making an agent actually do what you want it to do, debugging it, improving it. There's just a lot of slop out there. There's a lot of things that just don't work, or they work in proof of concept, but they don't work as you try to stand it up in the real world. So we'll talk a bit about one of the big problems in this and some of the ways in which we tackle it ourselves. Briefly, briefly a bit about us. As one of the largest observability and evaluation players out there, we work with some of the largest companies in the world use us to basically improve and troubleshoot, debug, and make their agents work. So think Uber, Spotify, Instacart, Bookings, Priceline, Discord, Etsy, all use our software every day to make their Gen AI applications actually do what they wanted to do, their agents work. And including large companies like Vanguard and Pepsi. So we see a lot. We see a lot of problems. These are a common set of things that I see. So first off, no planning. Probably the biggest bang for the buck if you're building an agent is planning. We added planning to Alex, our own assistant. It is a huge unlock. I would say mispruned context is another big one. Tools and adding tool calls, missing tool calls when you need to break up and make your tool calls a little more modular, another big issue. But the one I'm going to talk to today is the one on the right, which is feedback loops to improve your system prompt, and how to automate feedback loops to improve your system prompt. So that's the big idea. And it's not just our idea. So how many of you had caught the Karpathy YouTube video with talking about the Twitter video maybe a week or two ago? Anyone? Okay. It's great talk about the space and where we are. Highlighting constantly by Karpathy is the idea that people are in a lost direction on RL. So all of you here, there's a lot of you RL people here today. You should think deeply about this. So this talk's going to compare RL to what you can do in prompt feedback loops and the differences. So it's not just us, but basically his point is that a lot of these applications are a little bit like Memento. How many of you have seen Memento? Okay. So basically, what Memento is this guy's got short-term memory. So every day he's trying to learn his life again and basically writes on his chest the things that happen so he can piece together what his life is like. And building with LLMs are a little bit like that right now. It's a lot like Memento. And the challenge is your system prompt is static and it's not learning constantly from the mistakes from yesterday. Your instructions are not getting added automatically or in some semi-autonomous fashion. You're manually adding them on, scratching in your chest, what it should fix. And so the big idea with system prompt learning is feedback loops. Those of us who built a ton of things in control systems or RL realize the power of feedback loops. Feedback loops with text are incredibly powerful, and I'm going to tell you why. I would argue, much more powerful than a scalar number feedback RL. So we'll talk a little bit about that now, of what this is, how it works, what it's different. So if you've seen I guess how many of you use Claude Code these days? It's pretty awesome. The best agents out there, Claude Code Cursor probably, the best examples of highly functional things that help you in every day. This is an example of their linked prompt. Their prompt linked, on the internet. The prompt is massive, like absolutely massive. And it's not a surprise it's massive. There's incredible amounts of instructions in there that guide it on what to do in different situations. And those instructions are a lot of times probably manually entered, and maybe they're using automation, but the reality is the future of AI and AGI and these systems is not manually entering instructions and prompts. But this is what you're going to need to get to build an incredibly robust agent system. So let's talk about how do you get here with some automation. So traditional RL tends to be, and so how many of you do traditional RL here today? Okay. Don't get me wrong, a traditional RL I think has a massive place in a lot of systems and isn't I'm not the anti-RL person here, but I think there's a lot of problems with it. And a lot of problems, one of the problems is you've got a scalar reward. You've got an error term that's a number that it represents this error term that then upweights or downweights all the paths relative to what that problem was. And if it's a big path, you're updating mistakes it made and good things it did all together in the same way. You've got, Karpathy talks about RL as pulling feedback through a straw. And the straw also is it's a number. It's a single, there's no explanation of what the problem was. You've got, your reward is a number and you're just weighting things up. So the straw is this thin piece of information that you're trying to pull back, and then you're upweighting all your stuff equally. So let me introduce, there's a concept of meta-prompting which came out, and meta-prompting is feedback loops using a prompt, but they kind of, I think, made a mistake in the beginning. They made a big mistake in the beginning, which was, the big idea was right, which is getting feedback into prompts actually editing prompts. But the eval path of this was a scalar reward. So it was almost machine learning-like. I would get my set of failure cases and have scalar rewards and aggregate them and feed it back. So hugely problematic. And what's the big idea? What is system prompt learning? And what do we see is that if you're running evals, so how many of you run evals today, LM evals? Evaluations, okay, quite a lot. How many of you run explanations or reasoning on those? Okay. Biggest takeaway if you're doing evals, use explanations and reasoning. It is the most valuable piece of the eval itself. Anyone can get a bad good, but the explanation contains all the information on why. And the key there is that those explanations, which we use all the time in our platform, are great ways to call it hand debug things, but a great way to feed back how to fix the instructions in the prompt in the first place. So big idea is English contains an incredible amount of information, much more than a scalar does, and can be applied in a feedback loop. And the other big idea is that you don't need to, with evals and explanations and these feedback loops, you can do it on portions of your path. You don't need a full path like you need for RL. You can break up your path into different tasks, different parts of your task. I've got 5 steps to get to my goal. I can break up each one of those and have eval and explanations that feedback to basically fix the prompt actions. And what is this? And how is this different? There's GEPA out there. So we released this publicly a week before the GEPA paper went out. GEPA, by the way, awesome, absolutely awesome, similar idea to this. It has a lot more to it, but this is there's a core feeling that the core magic is actually feedback and English. So GEPA uses English as the eval and has the same feedback loop. It has one addition of a prompt generation in front of this. So this is a much simpler form. And by the way, this is 1,000 times faster than GEPA, at least in the implementations we have. So this is this is it, feedback loops with prompts. Again, what does this look like? RL, scalar reward, feedback loop, upgrading all the paths at the same time. LM evals, English dense information feedback on what the problem is, and you can update this on different paths that are broken. So this, and I can promise you if you listen to the Karpathy talk, he's talking about all the labs testing this and doing this and trying to get this to work right now. System prompt learning, like, you know, this is going to be feedback, and feedback loops are just an obvious way in which you want to upgrade and update your prompts. What are different ways we would test this? So the first one I'll talk about is like coding IDEs or some all the rage. So what we decided to do was do prompt learning to improve the system prompt of an open source IDE, coding IDE called Klein. We did this on Swebench, which, by the way, is very saturated, and I think we have our own skepticism of results on it. So I think we're also testing against, we have Arize Phoenix, which is open source library for evals and observability. If you haven't used, it's like the open source Lang Smith, if you know Lang Smith. We are also testing this on PRs against our open source library too, to test real learning against a true repository. So what happened? What does it look like? We'll talk about it. There's like Klein has a plan and act mode. There's on plan mode, you can kind of plan out your solution. In act mode, you actually have to code it and test it. So like you can judge the answer separately, like was the plan and thing right, and then take the right action. So there's kind of two ways of judging this. In both cases, there's quite a bit of lift, and what you're going to see is like we can make a pretty lower level model like 4.1 as good as Sonnet 4.5 with just adding instructions to the prompt, to the system prompt of these. And my view too, so what does this look like and how does this work? Client can come up with solutions. I think what I see a lot is it's very easy to come up with a very specific solution. You can solve a problem. So in this case, I'm solving a problem. I'm solving a problem with a very, almost solving that very specific solution, but not the general solution. And so in this case, it's it's fixing that single case, but you're going to have these other values that come through. Like in this case, it maybe fixes none, but the value can be true. And like you didn't fix the general case that actually helps this work in a more general case. So long story short is Klein was making very specific changes, and instructions can be added to Klein automatically that make it fix the more general case and have it and basically have it tackle these problems in a different way. Very similar example here where this one is a very specific fix for NumPy, a value error, like just, hey, if this happens, throw a value error. But Python itself has a way of handling things, trying to do this not implemented result. So almost like a Python-centric way of handling this in a more general case. Again, a general versus specific is kind of what it's adding here. So how it's tested looks something like this: software IDE, you run it, you're editing the system prompts, you're generating solutions, and you're either looking at those and evaluating those in plan mode, or you're actually running those against tests in act mode. And what we do is there's a lot of things we do. We use an LM as a judge, which is just a prompt evaluating the written solutions. That also helps us generate those explanations of like what the problem was. What we also do is in the train set, we'll pass the actual solution in. So the explanation's looking at Klein's solution, and it's looking at the actual solution. It's coming up with general instructions that help Klein then fix a broader set of problems that will, broader set of problems that then apply to the test case in addition to the train case. Oops, sorry. So what happens? If you've been out there, how many of you have seen GEPA or used GEPA to date? Have you heard, how many have heard of GEPA? Okay. Oh, wow. Okay, so it's the feedback loops that's the magic. So you'll see these examples of GEPA, but this is system prompt learning, just again, a feedback loop. This is what we start with, like nothing. It learns a whole set of rules from that feedback loop, from understanding the problem, the explanation. The meta prompt does recommend, hey, find a general solution. Don't just do a specific one, but it builds an entire prompt of instructions. And on our repository, where we're testing this, and we have like, the guy who runs our open source projects, pretty has a set of rules and ways he likes to run it. It will learn instructions relative to that the way that repository wants to run it. So again, it depends on the data you're feeding in and how you're feeding it in. It determines kind of how the stuff runs. I'm just wondering my time. I'm good with time. Okay, I don't think there's anyone after me. So gives you an idea of how we run the. So we basically run the problem. We look at the solution. There's a set of evals for that, and there's a set of tests that test how it works. Benchmarking wise, it's split across a train set and a test set. And again, the SWE bench, I actually think SWE bench is any of you who've kind of tested these eval benchmarks, you'll realize it's hard to get any edge because they're so saturated. Like the models have seen every example of these test cases in every single way. So getting edge is actually hard, and even on SWE bench is actually pretty damn hard. But it's incredibly clear to us from the instructions built out from this, the general software instructions that are built, that the potential is actually the potential is huge and massive to do this right, but just gives you an idea that lift on train, lift on test, lift that's I think substantial for really saturated benchmarks. We also did BBH. We talked about saturated benchmarks. So we did BBH. I don't think you see very many people split out actually per test BBH scores. We did that here. And again, it's fast enough. We tested a bunch of other optimization approaches. It's fast enough to actually run this on BBH at, in minutes, less than an hour or something, where I think most other approaches, it's like a day or two to get results. So the stuff is fast. Again, it's designed to be fast in our set. And as you think about the system of the future, how does this build into your observability and eval platforms? We have, first off, for us, we believe online evals are really important. You should be, if you're building an agent, we build an agent in our system every day. I think we have one of the better ones out there. We have a 2.0 coming very soon. We run evals all the time, and the evals look at the evals are generating that explanation, they're generating that assessment of that action. And you're getting this off of every agent run, everything your agent's doing, every action it's taking. And what it gives you is, one, the ability to look at it and debug if you need to, but it gives you the ability to also automate the feedback loop to add those instructions back to your prompt. So you can add them back to your prompt, you can build test cases, you can test it. So really building agents that work is about, to be honest, just hard engineering. It's about building tests, it's about building systems, it's about building feedback and improving with those systems. More examples. I think there have some DSPy versus the original DSPy, not GEPA. I think it was Simba in this case. Tests against this. GEPA is going to have similar results. It's a very similar. Foundationally, there's similar ideas, which is feedback loops with English explanations. And lastly, where do we think the system goes? I mean, it looks something like this, where you have agents, you have evals. We have this today running. We run this every day. Humans that augment the system with annotations. You have systems that help automate instruction feedback. To be honest, in our case, we get these suggested instructions, but we do have a human go okay, does this make sense or not? It's not I just let our agent run open loop and get instructions all the time, but it's this automated system that we have of basically adding it. And the systems will get good enough that one day that person probably doesn't need to be there as often saying, I want to keep this instruction or not. But it's about building these loops that like make the thing better with feedback and evals, to be honest. So this, hopefully, any questions for the group? Phoenix is our open source eval observability library. It's, I think, one of the popular ones out there. And then you have Arize AX, which is our enterprise platform, which is kind of what anyone in an enterprise or larger business uses. You can start with Phoenix. I mean, Phoenix, get started today. And yeah, any questions? Cool. Go ahead. Yeah.
You can use the podium.
Thank you. We spoke about online evals. What about, are people also using offline? So like events are generated from like agent execution, and then probably there's offline batch inferencing loop updating prompts?
Yeah, that's it. So the general question here was online versus offline evals. And a great question. So the answer is yes. So just so that people understand, offline evals I kind of view as like a unit test bench. Like typically it's evals that you run a bunch of test cases over. Those test cases in our case, sometimes are sessions, sometimes are individual generations. But absolutely you can use like, it's kind of like your iterative loop that you're using to kind of like generate evals and kind of train, maybe initial training. The online case is typically, you're putting it into, putting it out there into production, putting it into the real world. You're getting kind of examples back from real world use cases. And normally what we see is like, just the real world's just, the state space is so much bigger than what you test on. There's just so many possible inputs that someone can make, so many questions they can make of your system. Very different than maybe traditional ML. And so online, you get a lot of samples that you didn't think about, you save them off, maybe you generate some synthetic data based upon the examples there. So offline matter, it's almost like your unit tests running in an iterative fashion. Online matter in that it's like what you're pulling back from production.
Hi, Jason. Thank you so much for sharing all these very useful tips. I'm just curious on like you test all these benchmarks, and is this kind of indicators of saying, hey, what kind of tasks are the one AI agents are good at, and what kind of tasks humans are, good at as a compensation? Like if a problem like lead code can be tackled by AI agents, like with one strike, then we say this kind of problem is like would be easier for AI agents than a human. Can I take it that way?
Yeah, I think right now it's a hard, like the question is like, what are agents going to be good at, and what are humans going to be good at, and like, I think the challenge you have right now is like, honestly, I think there is a tiny group of agents that are super usable, and there's a lot of garbage, like incredible amounts of garbage out there, and so we're just in the first inning of realizing where these things are valuable. We're building one in our platform. I'm seeing every day. I think there's an incredible unlock if you do it right. For just like if you use Claude Code or Cursor, it's just so powerful from a workflow. I don't think I've had a tool in my lifetime that's been as useful in just unblocking me from doing stuff. And I think there's a potential to do that in a lot of different SaaS platforms that have that data, that can have these workflows, but you're used to clicking around. And why do I need to do that? Like why can it not, take the steps just like Cursor does to go do what I need to do in that software? And the reason it can't is because building these things are hard right now. And so it's not like there's an easy button. And so your question's more of an engineering problem than it is a training problem on data. It's kind of my feeling right now. It's like, how well can I engineer this thing to work in a software platform to do the work for me? So I think there's going to be an incredible, like almost any SaaS platform that you see where there's a workflow, you should be able to accomplish those workflows with agents. That's kind of my feeling. Like that's at least a low-hanging fruit. You should be able to do a lot more than that. Things that we didn't think of. I mean, I think it was hard to imagine what the Cursor and Claude codes before they existed. So I think there's going to be a whole suite of things that we don't even think about that also can be tackled. I think there's, but yeah. So I think there's a set of low-hanging fruit that are, hopefully we see really good solutions come out soon for. Awesome. Cool.
Hey, thank you for the awesome sharing. And I have a question here. I might be playing the devil's advocate, but my question is regarding the robustness of prompt optimization method. So basically giving LLM access to editing its own system prompt. And I assume that it might put different things into its system prompt. And can you share some examples of failure? And probably like, have you ever observed things like things in similar to RL, like catastrophic forgetting or like model collapse?
Yeah, I think the good question is, the question's like, good to be skeptical. I think there's a lot of hype out there. I think a lot of getting this stuff to work is just, again, hardcore engineering. I see all the time instructions back that don't make sense. The example I keep giving is like, a lot of times it fixes something specific, like it adds an example in that's very specific to this failure, but like you really want the general problem. Like that is so common in this. Like in the meta prompt, we're really guiding it to not do that. So that's a super common one. I think there's a lot of, I think with a lot of things here, we're, again, just early stage. Like RL's had decades of time to improve these systems. I do think these feedback loops with prompts and approaches are going to see, you'll see a lot of research, you'll see a lot of approaches to, and a lot of, probably human intervention in the meantime to accept or reject, the set of instructions created. So answer is yes, lots of abilities to fail, but I can tell you we're building an agent every day. I could not build it without these loops. It would be garbage, and I think that's why you see a lot of garbage out there. People aren't using okay, this tool was called, well, let me look at the prompt, let me look at the tools, let me look at the production data that went into it, and let me ask GPT-5, why was this tool called, and suggest instruction back. That flow is the magical flow that is what's driving our innovation and what we're building ourselves. I would not be able to do it without it. And so and it's just a simple feedback loop with AI helping in the middle. And can you do that a little better on a little more data? Yeah, and sometimes I'm dealing with planning, which is multiple steps, and I'm like, well, why did it do this here? Well, it's because of the previous step. So sometimes you kind of need, just even looking at that one loop isn't enough. You kind of need to look at the 3 steps and go okay, why did this happen? Okay, the instruction here was wrong because it called this tool that then caused this problem. So I don't think you can really build these without that AI feedback. I don't think you can build them good, and that's what everyone's doing today, is building really bad stuff. I think you need those loops to. I couldn't find the instruction myself in a lot of these cases to fix.
All right, we got a couple more questions here.
I think you mentioned on one of the slides that sometimes you need to just add a new tool for the agent, or maybe the tool you use is too complicated for the agent, or maybe in even more general case, maybe the task that you are solving with the agent is just too complex, and you need to somehow decompose it into multiple steps, something like that. How can you detect that? And
that's a good question. There's your question's there's a lot of failure cases which may be how do you detect? And I think it's a good question. Some of these, you're right. I'll give you one that I've debated recently. Building an eval for is the tool. We have these examples where our first mistake when we're building our assistant was actually too much in a tool. And it's so funny because I see some examples out there where people say, put a lot in a tool. For planning to work, you needed decomposable tools. I needed it to be able to put the tools together to actually, and it puts them together in ways I never even thought, and so for one of the things I've been thinking about, and we've been thinking about internally, is am I missing a tool to do something, or should I break something up, or is the combination of these tools wrong? And right now it's humans, like it's us kind of looking at the data. Like, is there other, there's failure modes that right now is like architectural and it's not, LM driven in my loops. I don't know if we put the AI towards that and help solve that, like, can it recommend tools, or I've thought about an eval for that, like just build out one to suggest, do I need to build tools? Because that's constantly what we're thinking about. So yeah, it's a good question. I think the answer is some of these loops are going to be really good at like those iterative prompt fixes. As you put your planning together, you should put your tools together. Loop's really good. Thinking about the architectural stuff is still very human. Cool.
Hello? Yeah. Okay. So I'm not very catch up. You said the method you're doing this prompt engineering is better than JPA, that method?
Your question is how's it different from?
I just want to...
How's it different from GEPA?
Yeah, how's different from JPA, and if I want to use your approach, how to use it?
Yeah, so GEPA is English feedback loop, and then has a tree generation at the end of it. We don't have the tree generation. We also aren't doing this at a system level. We're kind of like one prompt in your system. And then the other thing we do is in our examples, in our stuff, we actually we have a highly parallel, our evals, and like we have a parallel run system that basically deals with the parallel generations at scale, which we have in Phoenix. We've had it for a long time. Our evals are really fast. So the biggest difference is that tree generation and the parallelization of the optimization loop. And my question is like, has always been like, we have a JEPA a comparison coming out. My whole question is that, is that tree generation even useful? Like, I'm not. I think the magic might be in the feedback loop. Like, so a lot of what we're trying to do is like, GEPA is like this big algorithm. Really, what's the core? What's the value? I think is all of us debating right now, and I'm suspect that it is just feedback loops in text. But go ahead.
I see. And how do you compare with the Microsoft did agent lighting? That one, prompting reinforcement learning.
Can you say that again? Which one?
Agent lighting.
I don't know that one. I don't know off the top of my head. And yeah.
I see. Okay. Thank you.
Sorry. Cool.
All right. Any more questions or one more? All right. Last question here for Jason.
Just a quick one. Is there a toy implementation out there of your approach we can play with?
Yeah. So we do have an open source version of this. It is coming into Phoenix as an official experimental piece, but I think the first release has example open source implementations of this. Shoot us a note into our community too, and we'll send you a link to that. So cool.
Thank you, Jason from Arize, on that fantastic presentation.